Alright, so lecture 25, we're going to talk about telescopes. Not in any great depth, but we'll talk about them a little bit just to try to understand them. And the first thing you should realize when you're talking about a telescope is that telescopes look at faraway objects, okay? Really far away. If something's really far away, right, whenever I draw the rays coming out of them, right, which I'm making go in all directions, right? If I trace this out really, really far away, some point very distant, like way over here, right, then all of the rays that arrive at this point, which I'll move, will appear to be parallel, right? Even another ray around it, right? So, over great vast distances, like distances across galaxies and stuff like that, the rays coming from distant sources appear to be all parallel, right? So, if I think about what does a lens do if all of the rays come in parallel, again, let me draw my positive lens like this. All the rays that come in parallel, right? What does that do? Here's the one going through the center. I'll say that the focus is here, right? Passes straight through because that's going through the center of the lens. And all of these other rays will, I'll have to move the focus, pass through the focus, right? So if they're all passing through the focus, if we wanted to say magnify that, because we know they're not all really passing through the focus, right? Because objects are never infinity away, right? That's the case if they're infinity away. If they're not quite infinity, they're a little less, which I know sounds silly, but by a little less I mean they're just really, really far away, so that you can think of them as approximately like that. What will happen is, so over here I've already drawn a picture where I've got a big lens here, which we're going to call, by the way, the objective lens, okay? And its focal length will be this distance right here. We'll call that FO for focal length of the objective lens. That's to this point right here. So you see the rays that all come in parallel, right, all get focused to the focus. But if they're a little bit not parallel, then what's going to happen is they're going to form an image just behind this focus, right?
Yes.
So, for example, this ray, right, which came in, should have bent. I don't know why I drew it like that. It should have been, sorry, almost parallel. So I'll kind of accentuate the not parallelness of it. See how that is coming in not quite parallel, but almost to the optic axis, right?
Yeah.
It's gonna, and then this is a ray that's going directly through the center of the lens, so it doesn't bend at all, right? And it too has a very small angle that it makes with the optical axis, right? So it's almost parallel to it, but not quite. And so you can see that it's going to focus back here. So if we want to make that image bigger, right, we already know how to do that, right?
Yes.
So the way to think about compound lenses, that's when you have more than one lens together, right, is you first work the first lens, okay? You find out where the image is, okay? Here's the image, right?
Yeah.
It's going to be right here. Now for the second lens, this is another positive lens, right? So this is, but it's of a shorter focal length. So this one, I want the focal length to be less, all right? So I'm going to just make a dotted line down here so we know where this is going. So that's this one. This one is going to go here. And so that we'll call F sub E for eyepiece. This we call the eyepiece, okay? E looks terrible. Let me see if I can fix that. There we go. Eyepiece, okay? So this eyepiece has a shorter focal length lens. I'm going to make this focal length line up with the focal length of the objective lens. This one is longer, but I can make them overlap by simply putting the second lens of the eyepiece, F0 or F0 or FO rather, plus FE. Add the two focal lengths together, that distance will be the distance that the eyepiece is from the objective. You see that?
Yeah.
And if I do that, what am I doing? Well, whenever I have a lens with a focus f and I image an object, in this case it's an inverted object, right? We already know what happens. If this inverted object is closer to the lens, then the magnification is about 1 to 1, right?
Yes.
But if it's really, as it gets closer to this focus, right, the magnification increases, right? Remember the virtual images that we drew, right?
Yes.
So, I can draw them again by considering this ray. I have to make the lens a lot bigger though. Okay. And so that would be like that. And then we can go, of course, through the center. That won't bend. And so all I have to do is backtrace this and backtrace this until I get way back here. And now I've got my non-inverted image. It's inverted here because the thing we were imaging was already inverted, right? So it's going to stay inverted. So there's my virtual image. So when I look at it from over here, right, these rays coming out seem to be coming from this point back here, right? So I see what appears to be a much larger version of this thing just beyond my focal point, right? So it's important, remember, that you want it to be over here because it's in this region. Whenever your object distance is less than your focal length, right, that's when you're acting like a magnifying glass, okay? And so the eyepiece is actually a magnifying glass. And so I've drawn the non-parallel rays in purple, forming they cross right here. So that's my little image of whatever this distant object is. It could be a planet, you know. It could be Saturn. Saturn's nice to look at in a telescope, okay? So you can see the moons. And its image is going to be right here, but it's pretty small. It's inverted, so it's upside down. Nothing I can do about that immediately. But if I put a magnifying glass such that the focus of the magnifying glass is beyond where the image is, then it's going to magnify, right? Actually, if I just get my magnifying glass and I move in on that image, I'll find a spot that works for me. I'll get the magnification that I find convenient or pleasing. But these are usually fixed, and so they fix it such that the focal length of the eyepiece coincides with the focal point of the objective lens, because anything that's not infinitely far away is going to form its image over here in this region, right?
Okay.
And so if the eyepiece is set up such that its focal length coincides with the focal length of the objective, then we'll always be able to magnify whatever image we get here, okay?
Okay.
Make sense?
Yes.
And so in that sense, a telescope is really just, think about a lens. It images just like lenses do, and we've looked at that a few times, right?
All right.
And then we add the magnifying glass to it, okay?
Okay.
That allows us to enlarge that image. Now it'll be upside down, but you wouldn't know it, right? How do you know that you're looking at Saturn upside down versus right side up? It's not like you can tell. But if somebody had a sign on Saturn, and from their perspective it was right side up, it would look upside down from here, okay?
Okay.
You can fix that, by the way, by replacing this converging lens with a diverging lens, okay? And they'll have negative focal lengths, and so you can flip the magnification around. But that's a more advanced kind of problem. We're not going to worry about that. Mainly, I just want to get across the idea of what a telescope is and how it works. The objective lens will be a long focal length, okay? You want this to be a long focal length, all right?
Okay.
And I'll let you think about, maybe I'll put a homework problem together that asks why do you want it to be a long focal length. Some aspects of telescopes we're not going to get into this year. This is, we're getting a little deep into the optics stuff, and I didn't really want to go too deep into it. I just want to, see some insightful principles from this principle of least time, right? See how these simple laws can tell you things about complicated objects, right? All of this can be done without any mathematical equations, by the way. You can use rulers. That's the nice thing about ray optics.
All
You can just measure it on paper. If you're careful in the way you draw things, you'll be able to predict and measure what these image sizes are and stuff like that just from using these very simple principles. But yeah, so there are other considerations that will lead you to say things like, well, the larger diameter this lens is, right, is going to be better. And the way to think of that is, well, you can collect more light, okay? Distant objects, right, the light is faint. If you want to collect more light, right, by using a bigger lens. Professional telescopes owned by universities and the government, National Institute, what's NRA, I think it's called. That's radio telescopes. I can't remember the organization, but they usually use reflective optics, but these are big. I don't know what the largest telescope that you can buy is that's using refractive optics. So here I'm talking about refractive optics.
All right.
You of course could design a telescope using reflective optics too. Copying this down, huh? Okay. Mainly you should try to be able to reproduce it just by thinking about it. So we've got a really long focal length lens here, right? And then a short focal length lens here, right? That's going to act like our magnifier, okay?
Okay.
And I will write down for you. So what does the magnification turn out to be? FO over FE, okay? And so here is kind of, I'm not going to derive it. It's not that hard, but it's not important for what we're doing. So here, if you want to make the magnification really big, right, since these are both positive lenses, right,
Yes.
these focal lengths will be positive. Okay, so these are converging lenses, right, like convex lenses and stuff, right? So these are both positive focal lengths. So, but if we choose a long objective lens focal length and a very short eyepiece focal length, you see that this magnification gets bigger, okay? So that's why these two are as they are, okay? But I think if you draw pictures, you can kind of see, why that would be, and that's something that you should definitely explore. All right, so next we'll talk about microscopes.